Hi, welcome to SETI Live. My name is Simon Steele. I'm the Deputy Director of the Carl Sagan Center here at the SETI Institute, and I'm joined today by Sanne Bloot. Welcome, Sanne, to SETI Live, and we're going to talk a little bit about this amazing, fascinating new object, pulsating white dwarf, that you've been researching recently. And before we start, just to say a little bit about where you're tuning in from and the facility you work at, which includes the LOFAR radio telescope.
Yes, thank you, Simon. So I'm calling in from the Netherlands today. I am doing my PhD here at Astron, which is the Dutch Institute for Radio Astronomy, or the Netherlands Institute for Radio Astronomy is the official name for it. And I am currently working on my PhD. The main instrument I use for that is, as you mentioned, the LOFAR telescope, which is a low frequency array. The core of it is here in the Netherlands, but there are parts of it scattered all across Europe, all working together to form one giant radio telescope spread out across the continent.
Cool. And this is a low frequency radio telescope. It's a radio. What makes a radio? Radio is a pretty low frequency anyway. So what makes this a low frequency?
So radio is pretty low frequency. In this case, this is basically the lowest frequencies that we can observe with radio. So the atmosphere absorbs a lot of different wavelengths, absorbs a lot of different frequencies. And specifically at the lowest frequencies, at some point the ionosphere just absorbs all of the photons that could potentially pass through the atmosphere. This cutoff, where that cutoff happens exactly, depends a little bit on the circumstance of that day. It depends a bit on the solar activity as well. But that cutoff is around 10 to 15 megahertz. And LOFAR observes from that frequency, so around 15 megahertz, up to about 170 megahertz is usually where we observe. So we're really reaching that lowest end, going down to the lowest frequencies that we possibly can, and then a little bit above that.
Okay. So this is the lowest you can physically, lowest frequencies you can, or longest wavelengths you can actually observe, unless you get above the atmosphere and build something on the moon or in space or anything. So that's
exactly
really cool.
Yeah. As long as you're stuck on Earth, this is the lowest frequency.
This is as low as you can get. Yes. So I think, tell us we were chatting a little bit before we went online about this discovery. And discovery is, you go out into the night sky or even in the day sky for radio, it doesn't matter. And you look up and things appear out of nowhere. Almost.
Yes.
Tell us the story of this discovery.
Yeah. So in this case, what happens is you look up, you have a goal in mind, and while you're looking for that, other things happen. So my PhD is focused on using radio astronomy, using radio telescopes to study stars and brown dwarfs and exoplanets. So stars and then their little brothers, basically the smaller objects, they're a little bit in between, and then going down to planets. This is what my main science focus is. Now, what we expect to see from stars and brown dwarfs and these types of objects is emission that is strongly variable at radio frequencies. That is usually, it turns on and then it turns back off again. But on timescales of somewhere around tens of minutes to maybe even close to an hour. So something that turns on and it's there for a bit and then it just disappears again. Now, if you do a normal observation, you will normally look at a piece of the sky for a few hours, and you'll combine all of that data together and you'll make one image out of it. And this is because if you combine more data, you collect more light, you can look at things that are fainter. And for most things, that works very well because most things don't turn on enough. So if you look at them for longer, you can see more light coming from them. When you look at things that do turn on enough, this strategy doesn't work as well because you're now combining all that data. So you're combining data when it was on, but also data from when it was off. So what I was doing as the main focus for my research is I take this data where we've observed for hours, and instead of combining all of that into one image, I split it up into pieces, and then I make one image per little piece of it to see if there are sources that appear and then disappear when I combine it. I make almost like a little video of the observation to see if there's anything that suddenly appears and then it's gone again later. Now, I was doing this because I was looking for this type of emission coming from stars and brown dwarfs that turns on and then it turns off. And then while we were looking for that, instead I found something that, well, it did turn on and off, but it was off for basically the entire observation. It turned on for 10 seconds and then it turned back off again. And it was very fast, very short, and very bright because I was still combining this data on a few minutes just to make sure that I was, if something was only on for a few minutes, that I would see it. And this thing was so bright that even when it was only on for 10 seconds and I combined all that data in a few minutes, it was still detectable. So we saw this source turn on and then back off again, but we didn't know what it was. So obviously when you see something like that, the first thing you go do is you go find out what it is. So we tried to look at it, try to see if there was anything known, if there was a known star there or a known source there. And we looked pretty hard. I looked through every catalog I could find of sources. I looked at every image I could find that had been taken of that part of the sky. And there seemed to be just nothing there. Everything just looked very empty.
Wow.
So we had a very interesting source because it was definitely showing very interesting behavior in the radio, but we had no idea what it was.
Yeah. So out of nowhere, this flash goes on and off, and this is of course a radio flash. This is a radio.
Yes.
You hate to use the word transmission because you instantly think, no, that's we'll go there later maybe, but so this is a radio emission out of deep space at some point. So what are the steps then? As you say, you looked in the catalogs, there's nothing there. What are the next steps in actually trying to identify where it is? Find out where it is before you know what it is.
Yeah. So the first step was we went through all of the radio data that we had on this particular bit of the sky to see if it did it again. Because if you see a flash like that happen once, then maybe it was real, or maybe there was something weird happened with the telescope, or maybe something happened nearby. Maybe someone didn't turn their phone off near a radio telescope. Things like that can happen. We were pretty sure this looked very real, but just in case it wasn't, we did go through all of our data to check. And we saw that it didn't do this flash just once. It actually repeated. And it repeated every once in a while. Like it repeated fairly regularly. So we didn't just see it once. We ended up seeing it in that one observation was 8 hours. And we actually saw it repeat 5 times in there. Now, it wasn't always as bright as it was that first time, because that first time was really bright, and that's why we immediately saw it. The other times, it wasn't quite that bright, but it was clearly there. So our first step was to go through the radio data and see what it was doing in there, if we could find it more often.
Yeah. So you found something in the middle of nowhere.
Yes.
And the next step, of course, is, and I think we do have an image of the source, don't we, that we can have a look at. And Beth, maybe we'll pull that up.
Yes.
So here it is. And so where we study this, I just want to welcome everyone for tuning in here. We got people tuning in from England, Bangalore, Quebec, Canada, Italy, Niagara Falls. So welcome everyone. Do let us know where you're tuning in from. So we look at this. This is a real astronomical image. We're going to see some artist impressions later, and I'm intrigued to know how you go from this to these artist impressions. And this is the process of science. So what are we seeing here?
So what we're looking at here is an image. This is actually taken with an optical telescope. This is a bit on the blue wavelengths. So this is still a wavelength that we can see ourselves, kind of on the blue side. And this was data that was taken before. This was archival data. Someone had done a survey of the entire sky, and this data was part of it. But as you can see, this is just a tiny little blob. It really is only just a few pixels where you can maybe see that there is a source. So originally, this wasn't picked up as a detection because it was just a tiny little thing. It was quite faint. And they weren't really expecting anything to be there, so they weren't paying that much attention to this particular tiny bit of sky. But obviously, I just found a really weird radio source there, so I was studying every single bit of data I could find on it. So when we looked at this data very carefully, and we actually combined it with a few other observations as well, we saw this tiny little blob, and then we saw this tiny little blob in a wavelength that was a bit more green as well. So then we didn't just have it detected once, we had it detected twice. We picked it up once more. And that's when we decide, okay, if we see it 3 times, that's when you start believing it. Right? If you see it once, it could be maybe just a fluke. If you see it 3 times, then you're fairly confident that there is actually something there. But yeah, this is a real astronomical image. When you think of astronomy, you see all these beautiful images out in the news, and sometimes your images do look like that. And sometimes they look like this, where you just have a few pixels, just a few photons hitting your detector, and that's your source.
And this is the important thing for scientific verification. Just because one telescope just sees something, detects something once, that is not even proof that it's real. As you say, it could be somebody's cell phone or a microwave oven going off that's causing this detection, and that's happened in the past. So the fact you've now independently verified its existence through multiple telescopes means that this object is real. And so you've got an optical image, you've got radio pulses.
Yes.
What's the next step? You're building up a picture here, aren't you, of what's actually happening?
Yeah, exactly. So the first step is gathering your data. And then after that, it's trying to figure out what that data is telling you. So in this case, we had our radio data that was telling us that there was a source there that was producing these bright pulses, these bright flashes that were repeating periodically. They were regularly coming back. And we now had our optical data that was telling us that there was a source there. And when we looked at the colors of that source, so we looked at it in a few different filters. We saw a few different wavelengths. The colors of that source matched quite well with what we expect a white dwarf to look like. So I was looking for stars. I didn't really find stars, but a white dwarf is what is left after a star of about a medium mass has lived through its entire life, and it reaches the end stages of its life. It's not massive enough to go into supernova, become a black hole, but it does do a supernova. It just becomes a white dwarf instead. So it's not quite going to be compact as a way that a black hole or a neutron star is, but it is a stellar remnant after a star has lived its entire life.
Right. So you've discovered this, it fits all the patterns of a white dwarf. As you say, white dwarfs are the remnants of a sun-like star.
Yes.
After it's lived through its life cycle. They're about the sizes of the Earth, aren't they? White dwarfs. So these are small, but very, very hot. So even though they're tiny, you can see them because they're very, very bright because they're hot.
Exactly. And this one in particular is actually quite hot. So we don't know exactly how far away this one is. We can estimate its distance. We haven't been able to fully measure it yet because it's quite a faint source. But what we do know is based on its color, you can tell how hot something is. Right? It's even, you can tell how when you heat something up, its color changes. In the same way, when a white dwarf is very, very blue, it is very hot. If it's more on the red side, it is quite a lot colder. And this white dwarf is actually very blue. So it's very hot. And based on the distance estimates that we have, we can sort of combine that temperature with the distance estimate that we have to estimate how large it is. And we actually think this one is quite massive. So quite on the large or on the massive side.
Okay.
So
can I ask what is the estimated distance? So roughly, what are they coming out at?
So the estimated distance that we have at the moment is roughly 1 to 4 kiloparsec.
Okay.
Or about 3,000 to 14,000 light years.
Okay, that's a reasonable distance, isn't it? Yeah.
It is quite far. This is also why the follow-up was slightly more complicated, because this is quite far, and obviously that makes it quite difficult to see a fainter source.
Yeah.
So yeah, we're very happy that we did pick it up.
So going back to the results now, you got a white dwarf star that is pulsing in radio.
Yes.
And I think when I think of stellar remnants pulsing, I think of pulsars, which are neutron stars. They're not white dwarfs. So what is the mechanism that you have discovered, understood that well, and what do you think's happening?
So we call these class of sources long period transients because they are transient sources. They turn on and off, and they have periods that are much longer than pulsars. So very creative naming process here, but it describes them very well. And when we found the first one, this was published a few years ago, the first interpretation was, oh, it must be a very slow pulsar. It must be something like a pulsar that is just slowed down significantly. Maybe something is actively slowing it down, or maybe it's very old. Maybe it's just been slowly getting slower and slower over millions of years, and now it's just a very, very slowly rotating pulsar. But when you think of that, when it's that old, it doesn't quite have enough energy anymore to produce radio emission like this. Like the models that we use for pulsars that are spinning much faster don't work that well when you slow everything down so much. So at first we thought they look like pulsars, but just very slow. Maybe that's the explanation. Then maybe it might still be the case. We haven't been able to prove that there's absolutely no way to make it work, but the standard theories that we use don't seem to work that well when you get pulsars normally spin around in seconds on that order. These are more like minutes to hours, so they're much, much slower. And the standard models just don't work that well when you get there. So at first we were just very confused about what these things were. But then about a year ago, there have been a few systems where we saw these slow pulses, and then when we were able to follow them up and actually try and get very good optical data on them, they also spotted this white dwarf there, where they saw there was a white dwarf at that location. But in those cases, they also saw that there was a star there. So it was a white dwarf in a binary system with a star, and they were orbiting each other. Which is fascinating because white dwarfs are there, because there's quite a lot of them in our galaxy. They're quite common. But we've never seen an isolated white dwarf, so a white dwarf that's just by itself produce radio emission. And with how many there are out there, if any of them were able to do it, we probably would have seen it by now. It would have shown up sometime. But we've never seen that happen before. Okay. And now we have these sources where we do see a white dwarf that is producing radio emission. But every time we see this, there is also a companion with it. There's also a star that's orbiting it, or there's something else there.
So this is getting more and more complicated now. So we start off with
yeah.
And thank you. We got some questions rolling in. Good, because there are lots of questions about this. And welcome a few people from Knoxville and Virginia and Sweden as well. So welcome. So we got a rotating white dwarf radio emission, but it's not alone. Suddenly, there's something else there.
Yeah. So we think that it's interacting with its companion, with the star that is around it, and that is producing the radio emission. Okay. So that somehow it needs that star to be there as well, and that's powering the radio emission. Okay. Now, there aren't that many long period transients that we've discovered yet. We're at around 10. Mm-hmm. It depends on how exactly you count, but there are around 10 of these systems that have been discovered now. And not for all of them have been able to find a counterpart, and we've not been able to find an optical detection for all of them. But for the ones where we have been able to find it, there's always at least a white dwarf there, and usually also a star. So it looks like it's that interaction between the two that is causing this radio emission. Okay. But then going back to the system that we found, we only saw the white dwarf. We didn't see anything else there. We looked for it, but we didn't really see it.
So, I think we have an image of the thing we think is there, and we should need to bring up. There it is. Yes,
there it is.
This is isn't the universe beautiful? So there's nothing there. Basically.
Exactly. Yeah. This is so. When we were looking for the star, we decided to go look in the infrared because a star is usually very bright in infrared, and white dwarfs are not. Mm-hmm. So we figured if we see anything in the infrared, then it must be a star and not the white dwarf. So we got a very beautiful infrared image. If you look out, if in this image, there are many other sources that I cut out because I want to show that we didn't see this one. But as you can see here, we looked at it for several hours and we did not see anything. Mm-hmm. So that's the other side of astronomy. Sometimes you get a beautiful image, sometimes you just get a blob, and sometimes you get nothing at all. Mm-hmm. In this case, what this tells us is that if there is a companion in this system, like with all the other ones that we've seen, then it must be a very tiny, very low mass star, or maybe even a brown dwarf. So the lower mass stars People call it a failed star. I think that's a little mean towards a brown dwarf.
Yeah, I agree.
An object that's too low mass to do its own hydrogen fusion, so it's not as bright as a star. You can also think of it as a very large Jupiter object.
Yeah. So you got this transition, haven't you? We think of stars and we think of planets, but there's a smooth transition between the smallest stars and the biggest planets. So this is like a giant Jupiter as much as it is like a tiny star.
Exactly. Yeah. And those are fainter than stars are. So you could maybe hide one of those in that image. We wouldn't be able to see that.
Okay. So we've got all of this information. We got optical images. We've got radio. We've got a pattern that's emerging from the emission, and so that allows you to build a model of the system of what you think it looks like, and then you can test that model to see how the observation works. And we have and emphasize this after we saw the real images, an artist's rendering of this system, and it would be fun to bring that up now, and we can talk about what we think is happening here.
Yes. So this is an example of what we think a long period transient system could look like. So I guess I'll start with the white dwarf in the middle there. So we have the little white ball, that's the white dwarf. You can see it has a very strong magnetic field, and it has a companion there as well. So in this case, it's been drawn as a star. So you have a star that's orbiting around the white dwarf, and it is activating the white dwarf. You can see we've drawn that here as the purple lines. It is sort of pulling on the magnetic field. We tend to think of it as plucking a string. It's passing through a magnetic field line. It's sort of pulling on it. It's activating it. And because it's doing that, because it's activating that magnetic field, that produces a pulse, which has been drawn as that wiggle that we see coming from the magnetic field line going towards the Earth, that we can detect with LOFAR, which actually has been included in the artist's impression in the corner there. You can see
it's
LOFAR
down on the ground. Yes. Yeah. We have to emphasize this is not to scale.
It is not to scale. No, that is correct.
So we got the system. We got the white dwarf, which is roughly the size of the Earth. We got this brown dwarf star, which is, let's say, like a large Jupiter. So that gives us an impression of the scale of this system. And then, as you say, it's thousands of light years away from the Earth, and so these radio waves are traveling through space. Is the suspicion that it looks as though from this artist rendering that material is being drawn off of the surface of the brown dwarf, and as a sort of accretion disk, and this is the driver?
Yeah, that is one of the theories that we have. Now, for our system, we haven't even fully confirmed that there might be a brown dwarf there. We can't rule it out. And we do think that there is a companion, but we don't see it yet. Now, what we do see is, I think we need to go back a little bit here and go to the radio detections that we have. So we see these pulses that we detect, and we see them repeat in regular intervals. So they come back at regular times. But we don't always see them. So they repeat at a period of about 800 seconds. But what we see is that if we see a pulse, then you would expect to see the next pulse about 800 seconds later, because that's usually how these types of systems work. That's how pulsars work. They rotate, and then you see the beam of the emission crosses your line of sight, so you see a pulse. It rotates, and then the beam crosses your line of sight. Again, you see the second pulse. That's what we would expect, that it just repeats every single time the white dwarf rotates. But what we see instead is that it rotates once, and we see a pulse. Then it rotates again, and we don't see the pulse. It rotates again, and we do see it. But there's a very specific pattern in when we see the pulses and when we don't see the pulses. Specifically, we see 2 pulses out of every 5 that we would expect. And at first we thought, okay, sometimes, the pulses are not always equally bright. So maybe one was just really bright and one was just a bit faint and we didn't pick it up. Maybe sometimes you miss one. But it was always the same pattern. It always came back exactly the same way. It was always those 2 in 5. So what we ended up coming up with to explain that is that the beam is not only determined by how the system rotates, but is actually being pulled in the direction of the companion just a little bit. So if the companion is in the right place, then it's pulling the beam towards us, towards our line of sight, and we can see it. But if the companion's on the other side, it's pulling the beam away from us just a little bit, and we won't see it because it's just not going into our field of view, basically.
Okay.
So we think that there is something going on there just from the radio pulses that we see. Just from that, we think there is some interaction happening. Now, the other thing we see from the radio pulses is that the rotation of the white dwarf is accelerating a little bit. Now, normally, if there's nothing else in the system, if nothing is affecting it, then you'd expect it to slow down. Because it's losing energy, it's producing this very bright radio emission, it's sending all this energy out into the universe. So if anything, it should slow down. But this one's speeding up. And one way you can make a white dwarf speed up like this is if you, like you were describing, you're pulling that material out of the brown dwarf or the star, and you're dumping that onto the white dwarf. You can accelerate it that way. So we don't have any direct evidence that there is a brown dwarf or star there. We don't see it, but we have indirect evidence. We see that the radio emission is doing something weird, and we think that it's affecting the white dwarf rotation, possibly.
Yeah, and this is the fascinating inference you can do with the limited data. As you say, you've got a combination of the pulses due to the rotation of the star, but then if that white dwarf is also orbiting another invisible companion, you can see the effect that this invisible companion. That's how a lot of black holes, of course, are discovered, because they're the invisible companions to visible stars. Exactly. And then you can build up a picture of the system. I know we've talked about this for hours, but I'm gonna look at some of the questions that have come in from people tuning in. And I'm gonna I'm sorry if I mispronounce your name. Esatu asked, how unique is this discovery? Are there other instances of white dwarfs or other stellar remnants exhibiting similar rhythmic emissions?
Thank you. That's a great question. So I think I've mentioned this, right? There's about 10 systems that we would describe as long period transients, which means that they do these types of radio pulses on very long periods. Out of those, there's been, I'm fairly certain I'm correct on this right now. There are 4 systems where there has been a white dwarf that we've seen. So we're fairly sure that for 4 of these systems, there's a white dwarf there. For 2 of them, it has been fully confirmed with like spectra, and we've done everything we can to confirm it for those. For the other 2, we are fairly sure. And so, yeah, that's about 4 in 10 or so systems at the moment. Okay. Now, with those rhythmic emissions, like you're describing, repeating pulses, that's 10 systems, or about 10 systems at the moment. But these pulses are only happening 2 in every 5 pulses. That is unique to this system. We've only seen that once. That's very exciting. So I suppose, one of these questions is this very rare, or have you just started to learn how to search for them? Because sometimes, once you know what to look for, these things are appearing everywhere, and so that's probably the next phase in this exploration. Yeah. So this is the part that I'm personally very excited about, is we are really just seeing a tip of the iceberg with this field. These sources, because their pulses are so short, if you don't know to look for them, you could just completely miss them. So we are currently finding out whether these sources are by themselves very rare, or whether we were really just not looking for them at all. Now, I can tell you that I was not looking for these sources, and then they still suddenly showed up. So I'm hoping that there will be many of them. They are very interesting objects to study. So I hope they will just be around every corner as soon as we start looking for them. Agreed. Another question from Isatu, and we have to, because we're the SETI Institute, we have to ask these questions. We don't shy away from the tough questions. So sometimes we do. Given the precision and regularity of the pulses, could this be an attempt at communication from an advanced extraterrestrial civilization? So this system did many weird things while we were looking at it. The first time I found it, I thought we'd finally figured out this whole periodicity thing. I thought, okay, it does one pulse every about 4,000 seconds. And then it turned out that it did pulses every 800 seconds, but only sometimes. Then we looked at it in more detail, and sometimes the pulses themselves had very interesting structures. It started to feel like every time we had nearly figured it out, the system just threw something new at us. And it started to feel like it knew we were looking. But I do want to make it fairly clear that when I say that, I am joking. It feels like this. We have absolutely no evidence for this theory at all. It's more that sometimes it feels like your research is against you. And in this case, it felt like this object was just like trying to stop us from figuring out what was happening. Now, in terms of what you're describing of it being very precise and very regular, it is fully possible to create this with natural processes. Now, the regularity of the pulses, we see that in, for example, pulsars, where just because it's rotating very regularly, you see the pulses repeat very regularly. And the specific pattern that we see in it, you can also recreate that by just adding in that companion in the way that I described, where the companion's affecting the pulses a little bit. My theory would be that if this was an attempt at communication, the pattern would need to change fairly often in a way that was recognizable. Because if you make it too regular, it is impossible to see the difference between that and a natural phenomenon. So to be precise, the answer to the question here is we have no evidence of this, which does not necessarily mean that it's not the case, of course. It just means that I can't prove it.
Yeah. I think this is, the exciting thing about the universe is that it does throw these signals at us.
Yes.
That at first we have no idea how nature can produce them. And it's only after rigorous observation, analysis, and double checking, turning this weird little pixelated image into a model, that we realize that nature can do a lot of very, very strange things. And of course, this is the fascinating side of both SETI research and astrophysics research, is you try and explain what you're seeing. And you never know, but it looks like here again with this, like with pulsars and neutron stars, nature has created something just to mess with our heads, maybe.
Yes.
Maybe that's a sign of intelligence as well. But anyway, thank you, Sanne, very much for talking to us. It's been a pleasure. These are fascinating objects. We look forward, should there be more discoveries or more development of this, we'd love you to come back and talk to us some more about those. You are, of course, tuned into SETI Live. The SETI Institute is a non-profit research center in Mountain View, California, and we do rely on donations to keep us ticking over in the search for all things weird in the universe. Next SETI Live is this Saturday, which is coming live from Puerto Rico, where one of our telescopes, the laser SETI instrument, is being installed. Please do try and join us for that. There'll be details on our website. And until then, from Sanne and myself, thank you everybody for tuning in, and we look forward to seeing you again soon. Take care.